Everyone, we are Group 26. Today I'll be introducing our project for the distributed system assessment. Our project focuses on scalable password strength evaluation using a distributed computing approach. We aim to build a system that can process massive datasets of password efficiently using parallel processing. Let's start with the motivation behind this work. Despite new technologies, passwords remain the most widely used form of authentication. However, user habits are the weak link. People reuse passwords, keep them short, or use predictable patterns. This behavior creates massive risks. The Verizon Data Breach Report identifies poor password as a top cause for security incidents worldwide. Furthermore, IBM's 2024 report highlights that stolen credentials account for 16% of data breaches, with the average cost of a breach hitting an all-time high of $4.88 million. Organizations need to check their system for these weak passwords to stop attacks before they happen. So, why can't an organization just run a simple script to check these passwords? The problem is scale. In an organizational context, password datasets are massive. If you try to process this sequentially on a single machine, checking one password after another, it becomes incredibly inefficient. As the datasets grow, the execution time gets longer and longer. For a cybersecurity team effectively mitigating risks, waiting days for a report is simply not an option. We need a faster way. This brings us to the significance of our proposed platform, distributed computing. We analyze the problem and realize that password evaluation is perfectly suited for parallel execution. Why do you say so? Because every password check is an independent task. We don't need to wait for password A to finish before checking password B. To leverage this, we design a hybrid system. We use a central location for storage to handle the data, while separate execution environments process the task concurrently. This reduces the overall process time significantly compared to a single machine. Our overall plan for this project is to automate a sequence of dependent tasks to prove this efficiency. We generate a large sample of weak and strong passwords using Python for experimentation. Our workflow follows three specific phases. First, the split phase, where we break the massive datasets into smaller chunks. Second, the evaluate phase. These chunks are sent to multiple workers' nodes to be processed in a parallel against complexity rules. Finally, the aggregate phase, where the distributed results are merged back together into a concluding report. To conclude this section, our anticipated outcome is a fully functional distributed workflow that can process large datasets efficiently. The system will output a final summary report that clearly classifies passwords into weak and strong categories. Ultimately, we aim to demonstrate that distributed process offers a significant speed and efficiency advantage over traditional single-node processing, validating its use for large-scale cybersecurity tasks.
Hello, my name is Vishnu Govind, and today I'll be talking about the elaboration on our selected use case. So our primary goal is to evaluate millions of passwords in parallel, utilizing a combination of powerful tools and technologies to ensure speed, reliability, and data integrity. The four key components we focused on was HD Condor for task scheduling and resource management, DACMan for workflow management and handle task dependencies, Sandbox for job isolation for security and fault containment, and FS, which is a centralized storage for dataset and results. Moving on, now we'll be moving on to how these components come together to optimize our workflow. So HD Condor enables us to run tasks independently across multiple hosts. The loose coupling allows the system to scale efficiently. It provides better flexibility compared to systems like Slurm or MapReduce, which are more rigid in their execution. The HD Condor's class add mechanism ensures that tasks are assigned to the right resource for parallel execution, which will ensure efficient processing. DACMan, on the other hand, automates tasks for job scheduling. It handles complex dependencies, ensures that our workflow runs smoothly from dataset splitting to result aggregation. If any job fails during execution, DACMan automatically retries it, making sure the entire process continues without any interruption. The Sandbox plays a critical role in maintaining data integrity. By isolating each job, it ensures that any errors are confined to the job without affecting others. This containment helps keep the system stable and accurate throughout the evaluation process. Finally, we have the NFS server, which provides persistent centralized storage, which allows all execution nodes to access the same data, ensuring consistency. Additionally, HD Condor also manages all the file transfer, preventing bottlenecks that could occur if execution nodes directly access NFS during job execution. In summary, the integration of HD Condor, DACMan, Sandbox, and NFS create a robust and scalable architecture for our password evaluation system. This hybrid model ensures that each component is optimized to handle its specific task, making the system highly efficient and reliable even when processing millions of passwords. Thank you.
So I will continue the next session where I will talk about our implemented platform. So this is our architecture diagram. So first we'll start with the submission host. This is where we submit our workflow using the passwords.dat file. So the submission host does not run the computation itself. Its role is to just trigger the workflow and monitor job execution. So once the workflow is triggered, DACMan controls the job's order. It ensures the correct sequence. Split first, then parallel was password checking, and finally merging the results. So this guarantees that no job runs before its dependency is completed. So after the workflow is submitted, the DACMan will ask Condo Master, is there any available workers to run the job? Because Condo Master is the scheduler. It checks which execution hosts are available and decides where each job should run. So this is our NFS server, where our submission host and our execution host are mounted to it, so they share the same files. The NFS server acts as a centralized repository, but it is important to note that our jobs do not execute directly inside the NFS directory. So in this box, this is where the computation happens. In our system, we have two execution hosts, so jobs are able to run in parallel. So when the Condo master assigns a job to an execution host, the HCondo will create a sandbox. The sandbox is a temporary isolated execution environment created specifically for that job. So each job will run in its own sandbox, not directly inside the shared NFS directory. This is important because it prevents interference between parallel jobs and also to ensure that there's a clean execution environment to improve reliability and fault isolation. So once a job finishes, the sandbox will be deleted. So since the Condo master assigns jobs dynamically to any available execution host, the exact host selection may vary at runtime. So for explanation purpose, we assume that one possible execution flow is as shown in this diagram. So first, we assume that job A is scheduled on execution host 1. When the job is assigned, there's a sandbox created. So the split job will run entirely inside this sandbox where it splits the password dataset into 5 chunks. So once job A completed, the sandbox will be deleted, and then both execution hosts will be available at this time. So when job B comes in, which consists of 5 independent password checking tasks, it is scheduled to be in parallel across the available execution hosts. So for example, Condo master may assign the first task to execution host 1 again, since both of them are available. And then the second task to execution host 2, then the subsequent task again to whichever host becomes available first. So each password checking task will run inside in its own sandbox, ensuring isolation between parallel jobs. This dynamic scheduling continues until all 5 of these tasks are completed. So after job B task finishes, both execution hosts become available again. We then assume that, okay, job C, the merge job, will be scheduled on execution host 2. Then a new sandbox is created again, and then all partial results are merged into a single final result text file here. So throughout the workflow, the Condo master handles file transfer. Okay, it copies the input files from the submission host, which is also in the NFS server since they are all mounted, to execution host. And then once the execution host runs the job, the output file will then send back to the submission host. So as a result, once the final job completes, it will appear here, the final result.txt file. So these files will show the total number of weak and strong passwords, confirming that the workflow was executed successfully, which will be shown in the live demo next. So let's start with the live demo. I am currently in my submission host. So all the workflow files are stored in a NFS mounted directory. So let's start switching to that directory first. And let's see what files we currently have. So there are only scripts and also the job configuration files. This is because we hasn't generated any dataset yet or ran the workflow yet, which is why there won't be any dataset or output files yet. So let's start generating the password dataset. So this will give us a real-world password list for evaluation. So as we can see, it will be stored as all passwords.txt, and we have 700,000 of weak and 300,000 strong passwords. And let's see if... Okay, so this command confirms the dataset, which is 1 million in total, and this command shows like some of the passwords content to confirm if it's valid or not, which all of these are considered as weak passwords because there are no uppercase letter and it's in a very short length, and there's no special symbol used, and also my name's Shannon, and then I'm also using my name as a password, so it's obviously a weak one. So let's start with submitting the workflow and observe it. So as you can see, our workflow is running, though our first job is still in the idle state. Okay, it started running and then completed. So let's check. Okay, job B comes in and completed. Okay, even though job C didn't appear, let's check if the workflow, we can still check if the workflow really succeeds by seeing if we have the output files. So after the workflow completes, we can see that there are several new files created. We have this new chunks directory, logs, and our final result from the merge job, and each result of each of the chunks, and our Dagman workflow log and output and error files. So to see if our workflow really works is whether if we could see that the final result shows us the total weak and strong passwords or not. So let's find out. Okay, it works. So this just proves that we have a completed distributed system using HTCondor and DACMan, where it starts from splitting the dataset to checking each of the password in parallel, and lastly aggregates all the results together in a single output using cat final result to see if it works. So after the live demo, I would like to talk about the challenges I faced and how I solved them. So the first challenge was when I set up the AWS. So at the beginning, I used my own AWS account. However, during the setup process, my execution host unexpectedly crashed and I was no longer able to connect to it. So at first I terminated it and recreated the instance, but I failed to make it rejoin the HTCondo tool, which is why here it only shows one execution host. But then to avoid delaying the projects, I decided to quickly borrow one of my teammates' AWS accounts, which was stable and already functional. So I continued to set up the entire AWS using his account. But then before continuing, I actually overlooked an important step. I did not verify whether his submission host and execution host was actually mounted or not. So by the time I realized I actually already completed the entire thing. So I mounted the NFS server after I completed everything. And then I realized that once I mounted, all the files I previously created were no longer visible because the mounted NFS directory will replace the original local directory. But luckily, I didn't have to redo everything by recalling back because I had documented each step. So using this documentation, I was able to redo everything easier. So through this experience, I learned that NFS is quite important as a centralized storage layer because if in the future, what if I encountered some issue with submission host? I can't access my files there, but then because it's mounted, I'll be able to retrieve the data from the other two execution hosts. So the next challenge is that my jobs, when I tested my workflow, job B was all staying in the hold state. So after submitting my passwords.dat workflow, I checked I used the watch condor no batch command to check my jobs. And then I noticed that job A, it was able to run successfully, but then when it comes to job B, 5 of these jobs were staying in the hold state. So at first I assumed the issue was related to the file transfer configuration. So I'm focusing on debugging the password check.sub file, especially the transfer input files and transfer output files directives, because incorrect file transfer names can prevent the jobs from executing HTCondo, which is the next challenge. I will talk about it. So however, after further investigation, out of nowhere, I just used the lslist command to show what I have in my directory, and then it was just a sixth sense. I don't know why I did that. And then it was right, and then I found out that the problem was that the Python script password check.py was missing. So I think I must have accidentally deleted it during earlier debugging. So HTCondo could not find the script, and which is why all these jobs are on hold. So after recreating the Python file, I resubmitted the workflow and it was able to run. But then, even though it was able to run, when I cat final result, it says that there was no such directory. So the next challenge is this is a very confusing challenge. So during debugging, I also traced the issue back to the password check.sub file. So after the split job completed, all password chunks supposedly will store inside a chunks directory, which is what I mentioned during the live demo. However, the transfer input files directive was incorrectly configured. Instead of writing chunks directory, I was using an outdated variable, a $sign input variable. So it was actually an older version of the code and documentation, because initially I started setting up this AWS using 100 passwords only. So I did keep increasing it, and some files may change in some codes. But then for the 1 million, which is what our current one is, I actually used the previous code, which is why it didn't work. So after correcting the transfer input files to chunks directory instead, I was able to cat the final result.
Hello, I am Ethan, and here's the lessons learned and concluded section. So, this is the summary our group has come up with for the technical lessons we've learned from implementing a distributed system workflow. Through hands-on experience with HTCondor, DACMan, and NFS Server on AWS, we've gained a deeper understanding on how distributed systems operate just beyond theory. We saw how each component communicates and interacts with others to make the workflow function correctly. One key takeaway was realizing how fragile a distributed system can be. For example, files would disappear after mounting the NFS server, belts would go idle when a script was missing, and even minor configuration errors could disrupt the workflow. These experiences taught us that careful planning, strict configuration management, and attention to detail are essential. We overcame these issues with systematic debugging and repeated testing. So this slide focuses on our workflow performance, scalability, and teamwork. We've tested our workflow starting with 100 passwords, then 1,000 passwords, and finally 1,000,000 passwords. The system handled each increase smoothly, proving that it's very scalable and could potentially support even larger data sets by adding more execution hosts to scale. On the teamwork side, collaboration was limited. Tasks were divided mostly by report sections, while the AWS workflow setup was largely done by one team member. Despite this, the project allowed us to bridge the gap between theory and practice, reinforcing the importance of coordination, planning, and problem solving when designing and implementing distributed system workflows in cloud environment like AWS. Thank you.